Hello everybody, welcome to this third lecture in the foundation class series on physics, and today we'll be talking on a very important topic, waves and oscillations. You might have encountered simple harmonic oscillator before in your high school as well. We looked at examples such as that of a spring motion, of a pendulum, and there are other examples in which you can apply this periodic motion. For example, the motion of the earth that is going around the sun, and even the motion of a piston of automobile engines, the 2-stroke and 4-stroke follow this periodic motion of back and forth. And what is happening during this periodic motion? Okay. The body is moving back and forth about this fixed position, and this fixed position is called the equilibrium position. So like I was just mentioning before, the marble in a ball situation, at equilibrium the gravitational force is balancing out with the normal force that is applied because of the contact between the marble and this ball, and this is what we are calling as a stable equilibrium. And if you displace this marble from this stable equilibrium, then it will do the oscillations back and forth about this mean position. So we know that an oscillatory body will execute simple harmonic motion if the force, which we call the restoring force, acting on it is directly proportional to the magnitude of the displacement from the mean position. And this force, that is the restoring force, is always directed towards the mean position. So you can see the arrows, this force is always directed towards the mean position. So let's take an example of a spring that at the initial equilibrium condition, it is in the unstretched condition, and there is a mass m attached to the spring, and this spring is characterized by this spring constant k, which is a property of the spring which tells us whether this spring is going to be a stiff spring or maybe it will become a flexible spring depending on the value of k that you get. So in the equilibrium condition, when x is equal to 0, there is no displacement acting on this mass, so the force that is acting on this object is 0. So here we are considering that this mass is sitting on a frictionless table, and you have to keep that in mind as we go forward. Okay, so let's displace this mass now in the positive x direction, and if we do that, then there, as we know, there will be a restoring force that will be acting on this object, and that restoring force is proportional to the displacement and is given by the value minus k times x. And remember, we are considering positive x in this particular direction, so the force that is acting will be minus of kx because it's in the opposite direction. So the displacement that we are doing on the object is a. So if we stretch the spring until this point and let it go, because it's a frictionless surface, it is going to do the oscillation motion back and forth. So you can see the third situation in which the spring is completely compressed, and now the force has changed direction. So the force is pointing towards the positive x direction, and again the spring is going to stretch and go back and forth between these two positions. So when we say that this is a simple harmonic oscillator, time period to do a complete oscillation from this particular position all the way to the negative position and back to the positive position, that is one complete oscillation, that time period is fixed. So that time period does not change over period of time, so it remains the same. So you can look at some of these conditions that are given in the bottom. You have the situation that when the mass is on the left end, the displacement on it will be minus a, and when it's in equilibrium, the displacement is given as 0, and when it is in the middle situation, then the displacement on it is a. And we can also infer that the velocity on this object, because it is doing simple harmonic motion, So it comes to a stop whenever it reaches the ends. So the velocity will be 0 at the ends and it will be maximum at the center position when it starts doing the oscillation. And just by that correlation, we can say that the acceleration, we understand, will be the maximum when the object is displaced to the ends, and at the center position the least amount of acceleration will be acting on the object, and so you will get value of acceleration will be 0. So let's try to solve for this condition mathematically. So we can write down the Newton's second law, and the second law says that the net force acting on an object is equal to ma, and in our situation the net force acting on this object is minus kx. So that is the restoring force, and that is the only force acting on this object because it is sitting on this frictionless surface. The gravitational force is getting cancelled by the normal force, and that is in the y direction, so we are not considering that. Okay, so we can write ma in the form m d square x by dt square because we know that velocity is just the derivative of position with time, and acceleration is the derivative of velocity with time. So you get an expression of this form, and this will be equal to minus kx. And so you can simplify this a little bit further. You can divide both the terms by m and take the right hand term on the left hand side. So you will get d square x by dt square plus k by mx equal to 0. And this is a very important equation in physics. You will encounter it multiple times during your course of study, and it is known as the simple harmonic oscillator equation. Okay, so we want to find a solution to this equation, and to visualize how the solution will look like, you can think of a situation as shown here. So you have a particle that is doing a circular motion on this right hand curve, and if I am looking from the top view on this particular motion, so then I will project the motion of this object on the x-axis, and the projection on the x-axis from somebody viewing from top will look something like this, that the object is just oscillating back and forth on the x-axis. Okay, and this is what we are calling is the oscillatory motion. And this oscillatory motion, because it is doing a repeating motion and is periodic, as shown here, that it is periodic with the complete phase of 2 pi, then we can think that maybe the solution will look something in the form of a sinusoidal or wave, and that's where we begin with. So what we are going to do is we are going to assume that the solution to the equation that we have here, which is the simple harmonic oscillator equation, will be of this form, that the x that we want is of the form of a cos omega t plus phi. Show that this x is equal to a cos term is actually a solution to this equation. What we will have to do is we have to plug this x in this equation, and we will have to show that the left hand side is equal to 0, which is on the right hand side. So you have your term x, and it is given by some amplitude a times a cosine function of omega t plus phi. Here omega is the frequency and t is the time, and phi is just a phase. So because the particle can start from any angle as to begin with, right? So you can have a starting condition that the particle is at certain angle. For example, it is at an angle here, so that would be some 45 degrees or something, and it can start here, and you can call this angle 0. So that is just the starting phase. So let's take the derivative of this. So the first derivative of this equation will be dx by dt, and so you get a term which is a is a constant, and then you have to take the derivative of the cosine term, which is a negative of the sine of the term inside. So you get minus sine omega t plus phi, and then you have to take the derivative of whatever is inside this argument. So inside you have omega t plus phi, and phi is a constant, so there is no derivative for this constant, it's 0. and then you have to take the derivative of omega t. So it will be d by dt of omega t. So this is just omega. So you end up with dx by dt being minus a omega sine of the term omega t plus phi. Okay. Similarly, now you can take a second derivative of this term, and if you do that, you will get d square x by dt square on the left hand side, which is the term we want here, and on the right hand side you will get minus a omega, both are constants, so it will be as it is. And then you have to take the derivative of this sine function. So derivative of a sine function is just a cosine function with a positive sign, and then you have to take the derivative of the inside argument. So you again are given a value of omega from the derivative of this term. So what you get is, you get a term of d square x by dt square is equal to minus a omega square times the cosine function. Okay, but we know that a times the cosine function is just x. So what you can do is, you can replace a and cosine terms with just x, and what you are left with is d square x by dt square is equal to minus omega square x, and you can take this term on the left hand side and you get an equation of this form. And now you can relate this equation to this equation I here, and as you can see, d square x by dt square is the same, and whatever term is in the front of x, k by m, is actually omega square, and that is our condition. So if omega square is equal to k by m, then we can say that x equal to a cos omega t plus phi, this function that we have assumed, will be a solution to this equation I, and it will give us a resultant value 0 here. Okay, and from here you get the condition that the omega has to equal to square root of k by m, and that is your frequency of your oscillation. So the equation for spring motion is d square x by dt square plus k by m times x equal to 0. And remember again, if it is simple harmonic, that condition will only be satisfied when this frequency omega is square root of k by m. So from here now we can find the time period of this oscillation. So the time period of the oscillation will be 2 pi by omega, and if you solve that, you will get 2 pi square root of m over k. So this time period is the time required for one complete oscillation of the mass m that was attached to the spring, which had a spring constant k. At this point we should be aware that this condition that we are saying, that the force is a restoring force which is equal to minus kx, this is basically saying that the system is obeying the Hooke's law. So later you will be studying that this is a very limited case of which we are applying to it, and in this case we are saying that the potential energy is equivalent to 1/2 kx square of the system. And I want you to realize that this problem is a much more universal problem and can be applied to any mass and any spring system, and pendulum as well. It's even common in AC electrical circuits. If you're considering bending of beams, you can apply the same restoring force and find the equation of displacement. And these are approximate functions that are applied to the real systems. So later on in the higher level courses, you might have to use the non-linear restoring forces and include them in your calculations. So let's look at an example of oscillation in the LC circuit. Basically you have a inductor L, which is just a coil which has some turns that are wound like shown here, and then you have a capacitor, which is an element used to store charge. Current is flowing through this circuit. Because of the property of this capacitor, as we apply a voltage, there will be charge that will develop on this capacitor. So once we close this switch and we are saying that the capacitor was already charged, then the charge that was built up on the capacitor will start moving from this negative region to the positive plate. And so we will have a current that will flow in the circuit. Eventually you will get that all the negative charge will accrue on the top plate and positive charge will develop on the bottom plate. And again, this is the condition where now no current is flowing, and then this cycle will repeat itself, and all the negative charge will again flow back in the circuit and towards the positive plate. This motion of charge is basically similar to your oscillations that we were just talking about in a spring. And so you can do the calculations and find that this frequency of the oscillation of the LC circuit is given by a term that looks something like this, which is a square root of 1 over LC. We have been talking about just one oscillator up till now. That is, we have one mass and it is attached to a spring and it is oscillating. When you consider n number of particles that are oscillating, you will encounter a situation where you have to deal with waves. And waves are present everywhere in nature. You probably have experienced sound waves, light waves, there are water waves, and the definition of a wave is an oscillation that accompanies a transfer of energy through a medium. So generally waves are classified as mechanical waves or as electromagnetic waves, because mechanical waves require a medium for it to travel from one location to the other, whereas electromagnetic waves do not require a medium for travel. So in the rest of the talk we will be focusing on mechanical waves, and we will be discussing about longitudinal and transverse waves as well. So there are other form of waves, matter waves and gravitational waves, which are beyond this course, so we will not be talking about that. A wave is represented sinusoidal waveform as shown here, and there is an axis which is drawn, and this axis is the line that is running through the middle of the wave pattern. The crest of the wave is defined as the topmost part of the wave, and the bottommost part of the wave is defined as a trough. The amplitude of displacement is basically the distance from this axis at the center to the crest, and similarly you can take the displacement from the axis to the negative side. Again you will have the value for the maximum displacement. And at this point I want you to remember that the particle that is getting displaced in this wave is doing a complete oscillation. Suppose that the particle starts from this axis position, and then it will move all the way to this maximum amplitude 1, and then it will go back and perform the same motion and come back to this axis line, and then it will go back to the opposite side, that is this motion 3, and then it will come back to this middle point in the axis. So this entire motion is one complete oscillation. Maximum amplitude x will be given as the value when this cosine term is 1, and that will give you a value of maximum displacement as a, which is what we are calling is the amplitude of the wave. The wavelength is defined as the distance after which this wave pattern is essentially repeating itself. The wavelength lambda will be equal to this length from the point 0 all the way to this point 20. Another characteristics of the wave is frequency, and this frequency is defined as the number of waves that are passing through a point in space in each second, and it is generally measured in hertz. So let's look at what a period is. We defined it earlier that it is the time taken for one complete oscillation, and you can see here there is a particle, and what this particle is doing is it is performing the simple harmonic motion, and it takes about 20 seconds to form this complete oscillation. So right now it is starting, so it will go and displace all the way to the positive maximum displacement, and then it is going to come down and go all the way to the negative displacement, and then it is going to come back towards equilibrium position in the center. And while it is doing that, you can see that this wave is actually moving a distance of 1 wavelength, that is 1 lambda, during these 20 seconds. So there are some formulas which you should be familiar with. For example, if you are finding the energy of the wave, you can write it as h times frequency. F here is denotes the frequency of the wave, and h is the Planck's constant, and the wave speed v is given by lambda over t, or you can write it as lambda times f, because frequency is 1 over the time period. The waves, depending on the type of motion they have, can be categorized into transverse wave or longitudinal wave. And what is happening in transverse wave motion is that the particle is oscillating back and forth, and it is moving perpendicular to the direction of the motion of the wave. Okay, so this is a very important thing to realize, that the particle is not moving with the wave in the same direction. The particle is just moving back and forth about a mean position. What appears to us as moving, complete motion of all these oscillators, when they are put together, it appears to us that a wave is essentially moving through this material. In the case of longitudinal wave, the particle is going to move back and forth, but now the motion of the particle is basically in the same direction as the direction of the motion of the wave. So let's look at these cases much more closely. So this is your transverse wave motion. Again, your particle, for example, here is just moving back and forth, but if you look at this entire motion, it feels like there is a wave that is moving, which is a collective motion of all these particles. And like I had mentioned earlier, in the longitudinal wave, again, if you focus on just one particle, for example here, this particle is just moving back and forth about a mean position, and the collective motion, to us it looks like there is a wave that is moving. Motion of the particle about a mean position is in the same direction as the motion of the wave. So I hope these initial concepts are useful for you to understanding the motion of an oscillator and the wave motion, whether we are looking at vibration of atom or molecules, or even large size objects, calling them simple harmonic motion. Thank you so much.